Right, everyone. I would like to formally welcome you to our monthly Cape Center formal meeting. We've got the privilege of having Professor Thomas Jarrett join us tonight, and we're going to be discussing the topic of the quest to understand our local universe, the largest galaxies. I just want to make a slight adjustment to my screen before we continue. So I'd like to start out by telling you guys a little bit more about Professor Thomas Jarrett. So he is the South African Research Chair Initiative Chairperson in Astrophysics and Space Science, hosted in the Department of Astronomy at UCT. While he is world-renowned for his expertise in the near and mid-infrared, he also has hands-on experience in other bands of the electromagnetic spectrum, from radio to X-ray, both Earth and space-based. And he is a passionate researcher whose interest and expertise lies in extragalactic, large-scale and visualization of the nearby universe, large-scale structure, the zone of avoidance, intergalactic galaxies, star formation, processes, and galaxy evolution. He's now the lead scientist of the visualization lab at UCT, at the UCT Department of Astronomy, as well as the visualization research group at the Ezekiel Planetarium. Professor Jarrett, we would like to welcome you, and we are really keen to listen to your presentation tonight. I'm now going to make you a co-host. There we go. Okay. And you are free to start. Thank you so much.
Thank you. Thank you. Let me bring up my first slide and then I can kind of jabber on here. So I should be sharing. Let me optimize my video. And there, you guys should see this.
Yeah, we can see it. Thank you.
Stand by. Now I'm in play mode. Yeah. Okay. Well, thanks for having me. Good evening to you. It's just after lunch for me. So yes, I'm going to talk to you about galaxies. You're going to hear lots about galaxies. So be ready for that. And I'm also, let me just get to my slide where these are sort of the topics, the stuff that you'll hear about, the keywords: local universe, large scale structure, Milky Way and the local group, nearby galaxies, notably the big ones. And I'll do lots of infrared because that's how we've made headway with our science. I'll get to the physical properties of the top 100. And then this cool new diagnostic that I've invented called Pinwheel Diagrams. And hopefully I'll have time for that, but I might just blow over that. There'll be lots of lovely graphics and visualization that you'll see because I'm deeply into that. And so I hope you enjoy that. And some of you out there who are using very small screens, I don't think this will be too satisfying. But as you say, I guess it's being recorded. And maybe you can see that later. Okay, so that's what I want to do. My timer is on. I'll try to do 45, 50 minutes. And let's see how this goes. Okay, we're ready? So let me just ask the group, what is the largest galaxy in the heavens? Okay, now you don't have to yell it out because you know the answer, of course. But you might first ask me, what do you mean by largest? Because that could, there's various definitions for that. Well, let's just start off by, let's just gaze into the heavens. And this is something you all do all the time. And here's the answer. It is, of course, the Milky Way. It's the largest galaxy in the sky. And I'm showing you some northern and southern. And you're probably more familiar with the southern. And this last image shows, it's a beautiful picture. I think it's coming from New Zealand. And there's a lot going on here. You see all these stars in the background. This is be a really dark night in the Karoo. And you see the beautiful band of the Milky Way, and you see the inky dark clouds in which stars are born. You see the upper left, you see the Magellanic Clouds, which are little satellite galaxies that are in gravitational lock to the Milky Way. The Milky Way is in the process of eating them. They're about 50 kiloparsecs away. So you're seeing the top three right there: the Milky Way, the Large Magellanic Cloud, and the Small Magellanic Cloud. That's the big three in the sky. They're measured in many, many degrees across, and of course the Milky Way is everywhere. The other thing the picture shows is some aurora, and just to remind us that we have to work through atmospheres. And so we spend millions and millions of dollars to, in the case of the JWST, you spend billions, untold billions to get these things launched into space, so we don't have aurora problems. But we still have other problems. We still have to look through the solar system, for example, zodiacal light. Anyway, that's the top three. And what do you think number 4 is? Well, I'm sure you all know this, and I'm not sure you can see it from the Karoo. I bet you can. But there it is. There's number 4. That's Andromeda, M31. Beautiful. Just in this case, it's just below the Cassiopeia constellation. That's how I find Andromeda when I'm outside. I just follow the big W in the sky, and it leads me to Andromeda. Now you're going to hear a lot more about M31. Now here's another way to look at the Milky Way. This is coming from the WISE spacecraft, and WISE did all sky, so it was able to see everything. And you're now looking at the mid-infrared bands, and you can recognize the galactic plane. And we just passed the galactic center, and now you're looking towards the anti-center. There's M31 down there at the bottom here. Hopefully that you can see my little cursor. And some big off-plane star formation regions. Here's the plane. Here's Orion, perhaps you recognize it. Orion, the reason people love Orion is because it's off the plane. We can point our telescopes at it and we can go to town. Here comes the Magellanic Clouds, LMC, and around we come. And we're moving towards the galactic center. Up here is the Ophiuchus star formation region, Ophiuchus giant molecular cloud. Here's the galactic center, and so forth. So it's a beautiful view of our Milky Way. Now I'm showing you all of this because I want you to gain an appreciation of how hard it is that what I'm trying to do, which is to look at galaxies behind the Milky Way. And that's where this slide comes in. So this is the local universe. So we have to construct the local universe from our home world, from the sun, from the Earth, the sun, solar system, the Milky Way. And we have to look through into the universe. And we do this with imaging surveys, which are the most efficient by far. And we've been doing this all the way, since the Palomar photographic surveys. We do redshift surveys. These are fairly new and much harder to do, but you need them. We do standard candle surveys, such as working at Cepheids and galaxies. There you need space telescopes. And then you wrap it all up with reconstructive modeling, because you have to sort out all kinds of interesting biases and let's say observational effects that are in the way. Now, so I'm going to show you the local universe next. Let's just come back to the Milky Way. And again, I want to point out the most difficult part about the Milky Way. And you see it here. Here's a Gaia representation of the all sky. Beautiful picture they just came out with. But it's actually not too useful for extragalactic, because you're looking through all this junk. And for other reasons, I'll tell you why the optical is not the way to go. And there's a lot more there than just what the optical is showing you. If you look in the lower right corner, you'll see the IRAS, the far infrared view of the Milky Way. And you can also see our solar system, the zodiacal light in there. And you can see it is full of stuff. That's gas and dust. That's our beautiful Milky Way doing its thing, making stars, making our beautiful night sky. Now on the left, lower left, is the infrared picture, which can punch through most of that, and it can actually tell you and show you what's behind all of that, those curtains, and you start to see the stellar structure of the Milky Way. So now, with some magic I'm not going to go into, we were able to actually look through all of this stuff and construct the local universe using imaging surveys, redshift surveys, photometric redshift surveys, Cepheids, everything to create this sort of thing. So that is what the local universe looks like. Every little colorful dot you see there is a galaxy. And we're looking out to redshifts of about 0.2 or so. This is again, is just the local universe. You can see all kinds of cool structures in there. Let me see if I can find my, whoops. Where is my cursor? Wake up. Cursor, wake up. Well, I'll just have to describe it. Okay, so you see in the upper right there, that purple, that's the Virgo supercluster. And you can follow a line that goes all the way down into the plane. And where it stops in the plane, it's cut off at about 330 degrees longitude, it's galactic longitude. That's what's called the Great Attractor, because people noticed in the 1980s and 90s that a lot of galaxies were flowing that way, what are called bulk flows. And what that tells us is there's a local attractor. There's something that's big and massive. Okay, so anyway, I could go on and on about that, but what I really want to do is show you that in 3D. So a new way that we do that, that picture, which I created in the early 2000s, you know, we can do better now. We can go into 3D. So this will be my first movie. And to do that, I need to, let me stop my video. And this should work better. Okay, so now you're seeing the 2D local universe, which we are now, let's remove the Milky Way because it's in the way. And on to 3D. So now I'm doing this in virtual reality. I actually did this yesterday, but I have zillions of videos where I've done this on and off again. We're about 300 or 400 megaparsecs away in this instance because I'm using the 2-mass redshift survey. And I'm slowly moving in. I'm trying to go slow so it's not herky-jerky for you guys. And you're looking through my left eye. This is what my left eye sees. And I'm using my controllers to move around. I'm actually just sitting in my easy chair, but I can do all of this using my controllers, manipulate the universe. So we're moving around, looking at large scale structure. There's a cluster that's in our face there. And that was probably the Great Attractor, in fact, moving around. You can see the gap in the middle, that's the Milky Way. Here we're coming towards the local supercluster, which includes Virgo, which I'm about to point out. There's the Virgo Galaxy cluster, which is the nearest cluster, by the way. We're now within 10 megaparsecs, what I call the local volume. And down we go to 1 or 2 megaparsecs, and that is the local group. And in there, the local group is our favorite galaxies. Here's sort of our greatest hits. There's Andromeda, there's M33, and you see 55, 6822, and you see 147, 3109, 1613, and you know, there's many of them. There's 50 of these things, and they get fainter and fainter to the point you can't even see them. The big three that you saw there, M31, M33, and you see M31, M33, the Milky Way, yes. Don't forget the Milky Way. Okay, so I'm nice kind of moving around, and you can look at the large scale structure. I want you to notice the radial vectors that you're seeing there. Those are fingers of God, and that comes from motions of, extra motions of galaxies compared to the Hubble flow. You can ask me more about that if you want me to go into it. But that's why you get that stretching. I'm coming up to the, now we're at the North Pole, and that's the Coma Cluster. And it's part of the, oh, my cursor's back, the Great Wall that you saw up there. So the fingers of God. Okay, so that was a quick 2.5 minute tour of the local universe using VR. And there, of course, there's a lot more that we can do with that. And I won't go into that right now, but here we go. Now, while I'm at it, I should say that visualization is our thing, something that my lab does, and we love doing it. It's a lot of fun. But it's also the way to go these days, because visualization means you're using your brain, you're using your visual perception, you're using your intuition. And that's why it's important these days, because now the data is so large, what you call big data, and so complex. Machines are going to do a lot of the work for us, machine learning techniques and artificial intelligence, but you still need to take those, let's see, talk about the final products, the candidate, interesting objects, and you still need to actually look at them, and you look at them with every tool you got. So for example, we use the full dome at, there's Izico, and that the animation you've seen is coming from Izico, in fact, and you're seeing one of our Redshift samples in the background, a lot bigger one than you saw in VR. On the right, you see our nifty little machine called the Cobra, which is a little immersion tool that you can, if you have 3D or multi-dimensional data, you can immerse yourself in that. Anyway, my the lab site is down there below, and you can go see some of the cool stuff that we do. Okay, so let me just show you one more visualization. And here's M31, but maybe not a way you're used to seeing. This is the gas of M31, hydrogen gas. And this is called the Spectral Cube. And the Spectral Cube is three-dimensional. We have the two spatial dimensions, which this nice little picture, you probably recognize M31 there. And as we rotate around, the Z direction is the velocity, or the kinematics, which I'm showing you here now in 2 dimensions. And so that's the kinematic structure of M31. And that's one of the ways that we're using the visualization lab in the Meerkat era. This is now an important way of working with our data. Okay, I have digressed. I'm now 15 minutes in. Let's see. What exactly is the local universe? As I've been throwing this term around, and I'm not sure anybody's really thought about it much to date in this crowd, but I'll tell you what a rough definition is. It's simply this: as we look out into the universe, it is the space-time region in which galaxies have not appreciably evolved from their current state. The current means now, means us, 13 plus giga-years after the universe has evolved. So we're talking about galaxies that more or less are at the same state that we're in. And as you know, as you look deeper into space, you're looking back in time, and you're looking at a younger universe, and galaxies have different properties. They were smaller, they were probably warmer, hotter, they had less mass. Their gas content was higher. Their metals was lower, because they're just starting to build. And so what we see today in the Milky Way and in Andromeda, they've evolved for a long, long time. And so when we study the local universe, we're saying, the current state of things. Now, why nearby galaxies? So that's a good question. I get that one a lot. I even get it from astronomers. Because, these days, if you want the big bucks, the big telescopes, all the sexy, the grants and all the money that's going towards astronomy is for the high redshift universe. But the high redshift universe, as valuable and as interesting as it is, because you have to tie it into today, is also a lot more difficult to deal with. The galaxies, as you can imagine, are a lot smaller. They're different. And so we like to study galaxies in the local universe in order to infer what may be going on in the early universe. Let me get into that more later, but let me just show you a picture that I'm sure all of you have seen before. Why nearby galaxies? I think this really shows it. This was 175 years ago. Right, William Parsons, the good parson, Lord Ross, used his giant reflector for the time, a leviathan, and he did it from his backyard or wherever this thing was, looking through all that atmosphere, and he looked off towards this fuzzy thing, and he made this drawing. So this is really high tech for it today. Do this beautiful drawing, and it's a nebula, some kind of thing, and they had not. At the time, they weren't talking about island universes. That would come later with the big telescopes that they built on Mount Wilson. They didn't know what galaxies were. They weren't even thinking about it, but they knew there was something really special about this. Now, you know, if you had a modern telescope like what you guys are using out in the crew with your beautiful instruments, you know, through multi-band stuff where you can put it all together, you can create these incredible, beautiful pictures. And there it is. It's undeniable. It's a spiral galaxy. There's M51. So it's the Whirlpool Galaxy, which is a grand design spiral. And the Whirlpool is neat. I often talk about it with my students in my classes because you have its little companion on the right there, M51b, which is in orbit around M51a. And it's creating a tidal disturbance, and it's doing it in a resonant way. And it's creating this shock wave that moves through the arms and compresses the gas, and you get star formation. You get what's called coeval star formation, forming these very tight clouds. It's just magnificent. And you know, Lord Ross would have been blown away by what his picture is actually telling you. Okay, I could go on and on. I just love galaxies. So why large galaxies? Okay, so let's list some things that are good about them. You get the highest angular resolution, which means with our telescopes, space telescopes, really good ground-based telescopes in the high mountains, you can get sub-arc second, which means you can get parsec scale resolutions. Parsec scale means you're looking at stars forming, singular stars. That's a parsec. So you're getting down to the nitty-gritty. They have, here's the other thing, they have well-determined distances. Well, thanks to the redshift independent distances, you know, the standard candles, because the d squared term, 4 pi d squared in the luminosity is a killer. That's nonlinear. And so we have to do our absolute best to do, you know, get the best distances we can get. In the local group, you have environmental effects because we have other galaxies. You have M31, the Milky Way, M33, and you see you have various galaxies that are interacting with each other, and there's lots of intergroup gas, and so, you know, stuff is happening, so we can study that. Another one is the lowest mass galaxies, which are also called dwarf galaxies. They're by far the most common, but they're also the hardest to see. They're practically invisible. You can only see them at a few megaparsecs away. The very biggest telescopes with really long exposures can see them out to Virgo and a little bit beyond, but which is 20 megaparsecs. But otherwise, you are, you know, they're just nearby. The other thing is that multi-wavelength. So that's a very powerful way of doing astrophysics. In fact, that is the way that we do it these days. And the nearby galaxies have data going back to, you know, Hubble's day. And what I mentioned earlier is that they're local analogs to the high Z universe. And so that's why we constantly, you know, we're publishing our detailed work with nearby galaxies because people need them to understand what could be going on with the high Z galaxies, where it's just a blob, a blotch. That's all they got. And we have incredible time domain going back 100 years, you know, decades. So if you want to study things like supernovae and variables and so forth, that's the local universe. There, of course, is the mystery of what is near us and how it may compare to a more distant universe, which is called the Copernican principle. And I'll touch upon that at the end, because that was one of my experiments with my sample. There's, of course, lore and myths and dreams. And I do want to point this out, and maybe some of you know about this. This is just so cool. The first, it wasn't Lord Ross who recorded the first galaxy. It goes back at least 1,000 years to a Persian astronomer, Al-Sufi, and maybe even before that, but he actually published this in the Book of Fixed Stars. And he noted, he didn't know what it was, but he noted the little fuzzy thing next to the fish's mouth, which he called the little cloud or the small cloud. That is our adorable M31. That's Andromeda. And you might wonder what that fish is. Well, that was called the big fish next to the little cloud. So that is the actual constellation of the time, the big fish, which is now gone. This is the constellation of Andromeda. But I will note that Pisces is directly below the feet of this person. So there's that, and there's a challenge of doing it, which I'll get into. And then there's, this was in the news, the big collision. I should have capitalized that. The big collision, of course, is that it was noticed by Hubble and company, Slipher and those guys back 100 years ago that M31 Andromeda had a blue shift, not a redshift, but a blue shift, a few hundred kilometers per second. And now we know, if we take into account the rotation of the Milky Way, which is the sun's solar motion, we know it's about, the Andromeda's coming at us at about 120 kilometers per second. Not a direct hit, but it's pretty close. It's going to be somewhat radial. And you can see the trajectory there in my little diagram. You might wonder, when is that? Well, it's got to cover 730 kiloparsecs. That's how far away Andromeda is. And so it's going to do this little quickie, little tidal pass, gravitational dance, and then it'll merge, as I will show you in a second here. But anyway, if you use Newton's law of gravity and you use the kinematic laws of motion, you can calculate it. It's around 5 billion years, 4 to 5 billion years when this will actually happen. So, I wouldn't be too worried about it. Still, it's cool. We visualized this in the lab. So one of my colleagues, Nathan Degg, simulated this with an n-body simulation. Here he's got two equal-sized Milky Way galaxies. Andromeda is one of those. And he's constructed the simulated galaxies. And he's done the time domain analysis. And we put it into the virtual reality. And you can see him in the little right there. He actually has his headset on. He's got his little controllers. And you can see at the bottom there, that's him. That's the ghost waving the controllers around. He's pointing things out. He's actually talking into a microphone, and he's pointing things out. So he's watching 4 different particles for each galaxy. So there's 8 particles in total. There's a stellar particle. There's a gas or halo particle. There's a dark matter particle. And there's a bulge particle. And so he can see how the two are mixing. And we know that there might be some stars that are from Andromeda that are pretty close to the Milky Way. Why? Because maybe this interaction has already happened. And we're coming towards the second interaction. I don't know. But you could see that with the simulation, it's quite dramatic after that next pass, that we will do a little dance, and then we'll consummate the marriage, and we'll have a new entity, the Andromeda Milky Way thing. Okay, so that's the sort of thing we do in the lab. Okay, so what I'm going to do, and I'm going to jump, I'll get back to how we actually did these measurements, but I'm just going to show you the top 100. Let's get to it while I still have your attention. So let's do it. Here's the top 100 galaxies. Now I'm showing you a way of visualizing these galaxies. It's called 3-color RGB, which I know you all can do with your multiband photography and imaging that you do. This is the same idea, except we're now using infrared bands. So when you see blue light, that means stellar. That's the stellar backbone. Those are the old stars, and that's what holds the galaxy together. And when you see red, you're looking at new star formation. Those are the clouds that have been warmed and lit up by the star formation. So you're seeing combinations thereof. So at the top we have the LMC, SMC, Andromeda, and then number 3 is M33. And I think I'll just go through these. I'll point out some interesting ones. NGC 253 is the nearest starburst galaxy. And you'll see another starburst in a second. It's only 3 megaparsecs away. The next to it is NGC 5128. Well, that's also better known as Centaurus A, the famous radio galaxy. And yes, it's doing a lot. M101 might be the most beautiful galaxy in the sky. It's a grand design spiral face on. It's also really big. It's actually physically large. What else? I think that actually at the bottom there, I see 342. That might be even more beautiful than M101. It's a cracker. I don't think my picture does it justice. Now, one thing to the right of that is NGC 1360. I'm going to come back to that, but that's Fornax A, and he is the biggest in physical terms. He's the biggest galaxy in the sky, so I'll come back to him. Here's the next set, Mathi 1, recently discovered because it's in the zone of avoidance. M110, that's part of Andromeda that I think you can see from the ground with your telescopes. M104, that's the sombrero, beautiful galaxy. M87, lower right, the big famous Virgo A. So that's where the black hole was mapped with the Event Horizons telescope. That's M87, he's a monster. Here's the next set. Lots of pretty galaxies. They're getting slightly smaller. There's M83 in the left side. I'll come back to him. NGC 65822, that is a local group. And you can see he's ghostly and supremely difficult to measure. Really difficult. Why? Because the Milky Way basically is mixed in there. I mean, can you tell the difference between the galaxy and the Milky Way? Not very easily. So I worked pretty hard on that one. Next set, Mathi 2, again, recently discovered in the zone of avoidance. And you can see some galaxies have companions. Some are knife edges. There's the Whirlpool in the lower right. Next set, you're seeing a more variety of morphologies and different, there's some ringed galaxies, some disturbed galaxies like IC10, which is also a local group. Edge-on galaxies, NGC 891 at the bottom there, you can see a little red glow. That's edge-on. A little red glow around it, that's because it's got a pretty strong starburst and it's blowing perpendicular to the disk. Those are called super winds, and so stuff is getting blown outside into the intergalactic medium. Here's that, we just went past the halfway point. There's some more nice edge-on galaxies there. NGC 3109, that's a local group galaxy. I'll come back to 1365. That's the most beautiful galaxy in the Fornax cluster, just a gorgeous thing. At the bottom, you see Circinus Galaxy. That was also recently discovered. You can see how many stars you see there. It's right in the Milky Way, very difficult. But Circinus is special. That's the nearest AGN. So that's a Seyfert 2 galaxy. It has a big black hole engine and it's active. Some more beautiful galaxies. Here, M82 at the top there. So M82 is a nearby starburst, and you can see it's an absolute fireball. Beautiful galaxy, amazing. In the optical, it's nothing special. If you've looked at it in your telescope, you probably shrugged your shoulders, but if you look at it outside of that, you know, the more interesting bands, you would see this. It's on fire. M77, also known as NGC 1068, is the most spectacular AGN in my entire sample. He sticks out in every way. It's all happening in the nucleus. So that's unresolved. You're just seeing really bright nuclear light coming from there. Let's keep going. And here we're on the last set of slides. And you can see the last one on my list is NGC 5363, which is bluish. That means it's just an old galaxy, not much going on. Okay, all of this stuff comes from this paper, which we published in December, and it's online. It's an AppJ, Astrophysical Journal. You can go see. So now let me get to some of the science of why we're doing this. So here's the big picture of what we're doing. And it's more than just the top 100. We're measuring lots and lots of galaxies. And that is We're trying to characterize the local universe in a way that's never been done before, in a quantitative way. There are a lot of what are called samples. People have made their favorite sort of lists of galaxies based on certain properties. I've been measuring those lists. That was been my highest priority, so that I can get that to them. They can carry on with their science project. Now, we're also preparing for the SKA and the big hemisphere surveys, which are coming. And these include radio continuum. So the radio is just going to sweep across the southern sky and measure every galaxy that's out there out to the highest redshifts. We also have optical redshift surveys, the next generation. They're coming. We have H1, such as Meerkat, that are measuring things like the star formation, the gas content of galaxies, and using a method called Tully-Fisher. And you know, these are analogs for the high Z universe. And the other thing we want to ask is the local volume. Are these nearest galaxies, are they special in the greater context of the universe? Okay, so that's why we did it. And now I have to tell you why we do infrared. Well, we do infrared because it tells you something completely different about the physical mechanisms of galaxies and stars. This picture of Orion really shows it. There's what you see when you look up on the left, and on the right, if you had infrared eyes, you would see that. You could see there's a lot of action going on, gas and dust and stars. This is all part of the multi-wavelength agenda. That is to say, we use different bands and spectroscopy, which are just very narrow bands, to figure out what's going on. It's a big puzzle. There's a big crime scene, and we have to deconstruct what may have happened. And so we use all these bands from the ultraviolet, X-ray, ultraviolet, all the way out to the far infrared and the millimeter, submillimeter radio. Each one tells you something completely different. Now, the infrared. So most of this data is coming from WISE, which was a space telescope launched in 2010. It has 4 bands, and so all these pretty pictures you see are coming from these 4 bands. And 2 of the bands, what I call the near infrared bands at 3.4 and 4.6 microns, they are sensitive to the stellar mass. Okay, and so you see the backbone. At longer wavelengths, 12 and 22 microns, they are sensitive to the ISM heating. And so that is coming from the massive star formation. And we can use those two together effectively to construct the evolution of these galaxies. WISE was all sky, and so it sees everything. You have a measurement everywhere, and you can go to the archive and you can pick out the data yourself. In the mid-infrared and the near-infrared, you have all kinds of mission from stars and galaxies. You have photospheres, you have thermal tracers like the ionized gas, H-alpha. You have non-thermal coming from shocks. These are fine structural lines. You have dust grains, small, large, and everything in between. You have molecules like the polycyclic hydro pHs, molecular gas such as H2. These are the key science metrics that are coming from this data. We measure luminosities. That's why we need distance. Morphologies you can get from the infrared. The star formation rate, which is the number of stars produced per year in the galaxy. The stellar mass. And the stellar mass is basically what comes from the star formation. So it's the past history. And that's what we call the the galactic evolution. We also can understand AGN, which is really just a phase of big galaxies, and we can put it together with multi-wavelength data, multi-wavelength synergy. All right, I'm going to give you a science example that we've been working on for a long time, and that's M83. Spectacular, beautiful. This is Southern Pinwheel. I'm sure all of you have seen this. It's a great galaxy. I love it. I love it. Here's a nice, lovely optical picture, but it's not useful for science because it's basically what we call flocculent, and it's just showing you absorption from the gas and dust. And so we have to move to the mid-infrared, and so we use these more useful bands. And this is an example of the synergy between bands and the blues. So the magenta and the blue, that's coming from the Galaxy spacecraft. So it's the ultraviolet, which is sensitive to the young stars, the massive stars. They're 10 million years old. And then we have the WISE bands, where the ISM is heated by the ultraviolet. And you get this emission but it can last more like 30 to 50 million years, and even up to 100 million years. So it's a little bit older star formation, if you will. And then at the bottom, you see the near infrared bands, which is the past history. And then you put it all together and you get this really interesting picture, where some of the ultraviolet's getting out, it's not absorbed, but most of it is being absorbed by the gas and dust. Here's a spectral energy distribution that kind of gets into what is actually happening here. And SEDs, as they're known, on the x-axis is the wavelength. On the left, you're going from the optical ultraviolet, and to the right, you move into the infrared and beyond. And you're showing the flux of the measurement of the source. So you have this peak that happens in the near infrared. That's the H band, 1.6 microns. That's the old stars. That's the red giants. That's old. You know, they're solar type stars. And that's most of the mass of the galaxy. As you move into the mid-infrared, as you go down those curves, you start to pick up the ISM. And here I can show you a demonstration of what you might see from each galaxy. M81 is that blue galaxy there. M81 is a big nearby galaxy. It's sort of an SB type, and it doesn't have a whole lot of mid-infrared. But the M82, the starburst, which the two are interacting, and which is why M82 is doing its thing, because its gas is getting compressed. It's got a completely different signature. So we use this as a signature of the galaxy. And basically what's happening is you have transformation from the left to the right. So the ultraviolet from these young hot stars spews outward into the disk. So it's spiral arms, it's absorbed and re-emitted in the mid-infrared and the far infrared. And so you get these big signatures for most of the flux, the bolometric luminosities coming out there, and the sub-millimeter. Now the radio synchrotron that you see there, that's also tracing the young hot stars. So there's a real interesting connection between the left side and the right, which I won't go into right now. And so a thing that's important for us is the fuel for the fire. So we have gas being converted to stars. And so it's very important to study what the gas is, what its distribution is, and what its relationship is to the star formation. And to do that, we have to go out with our big interferometers like Meerkat, and we have to image these galaxies and get the gas distribution. And I showed you the kinematics of M31. So not only do we get where the gas is located, but we get its motion. So you're seeing an example with M83 on the left, and on the right is the star formation in the grayscale overlaid with the gas. You can see they're beautifully, nicely correlated. Because you need both, so they go hand in hand. This graphic just shows the whole thing put together. You're going from the fuel in the upper left to the fire upper right, to heating of the interstellar medium, and to finally into producing the stars, the old stars, and that's in the middle. So the mid-infrared is an excellent tracer of the star formation. And that was done in this work. So I'm just going to go very quickly through some work that we've been doing over the years and starting to pay off. And our research is actually picking up because we can exploit this calibration. For example, we know that the mid-infrared now, thanks to this work from Michelle Kluwer, some of you may know Michelle, who's now in Australia, that there's this beautiful, tight relationship between the mid-infrared and the far infrared and star formation. So we use that. That's a calibration that we exploit, and we exploit it in these various studies that we've been doing. Here's my student Elizabeth Naluminsa, who studied a sample of nearby galaxies with the WISP survey, which is H1, so that's radio. And she used WISE to understand the relationship between the two. And here's my student, Vaishali from, she's an Australian. She did this with a big southern sample. My other student, Jamie Bach, has been doing this with using a sample called alfalfa. and Amiga, and also using these WISE relations to do this. And our most recent papers come from my student, Mark Harris, who here he's using the optical spectroscopy and the infrared to see the relationship and how to separate star forming from AGN galaxies. This paper is so new, it doesn't have a volume, but it'll be out next month, I would imagine. Okay, I'm at 43 minutes, and now I'm gonna get to this is the part where I tell you how I measure these bloody things. So I guess I have to go through it fast. I have 5 minutes. So, you know, Carl Sagan once said, if you wish to make an apple pie from scratch, you must first invent the universe. And scratch is the key word there, because you got to start from the beginning. Now, the universe already exists. All we have to do is capture these galaxies with our cameras and measure them. So to find the largest galaxies, you must first measure everything. This is my catch-22. So you might ask, have you measured everything, Tom? And say, no, I have not. I have a ways to go, another few hundred years. But I could use a cunning shortcut, and that's to use our sky lore. So Charles Messier and NGC, people who've come before me long ago, these giants, I could stand on their shoulders and I can construct my samples. I know where the big galaxies are. I can build my mosaics from scratch because I pretty much make custom images. And then I do the hard part, which is measure them. And I measure them using various pipelines. You know, this is all the stuff that I do, my bread and butter. I'm not going to go into that. This is an example of how I'm measuring a galaxy with apertures, and annually you have to measure backgrounds, and then you measure surface brightnesses and so forth. Galaxies have like 100 parameters. I know that for the 2MASS survey, the galaxy parameters, we have something like 300 parameters or measurements per galaxy of various things that you can measure. It's out of control. So yeah, you know, you measure things, and I have these things. These are my summary cards. Every galaxy I've measured has this. So the summary of the photometry, its colors, a picture of what it looks like before and after I've removed the stars, and radial surface brightness, that sort of thing. We've got that. Okay. So I've measured nearly all the big galaxies. So we have 130,000 or so up to this point. All the famed M's and NGCs and UGCs, that should be a C, ICs and so forth are in there. However, I just want to point out that the biggest of the big, you have to use a completely different technique. LMC, SMC, M31, M33. I was not able to do that. I had to use the statistical approach to figure out what was going on in the background. And the reason is because Andromeda is so big and so spread out. As stars go out into the Milky Way, it's very difficult to decide, is that an Andromeda star or is that a Milky Way star? And so we had to use various statistical methods. But in the end, at the bottom there, you can see that's all the stuff removed that we don't think is part of Andromeda, including M110 and M32. I've removed them too. All right, and then you get things like these radial surface brightness profiles and the 4 bands, and you know, Andromeda is just so much fun. It's amazing, amazing galaxy. And just to remind you there, it's the little cloud. And look how look the little cloud. It looks just like what I've got there. Well, you know, pretty close. 1,000 years ago, we'll cut them a break. M33, left, right. You can see after we've determined what belongs to M33, that's what's on the right. Magellanic Clouds, man, look how hard this is. Just look at this picture. This is a 30 degrees across. This took me years to make. And you know, the LMC is just amazing with its bar. And do you notice that in the infrared, it's square shaped? It looks like SpongeBob SquarePants. Isn't that cool? It's actually real. It's the real deal. It's not a fake. So anyway, measuring that is difficult. If you run radial profiles across it, you can see that the emission is, you know, there's all kinds of stuff outside of that, of the galaxy. And then here's some of the results coming from it. Let me just go fast. I want to go to some of the physical parameters. Oh, first the color. We compare the colors of our nearby galaxies with 10,000 other galaxies that are not that far away to see if things are different. And I've plotted it on this plot. This is the 2 different colors you get from WISE, which are quite nice. But basically the upshot of all of this is that there's nothing that stands out except for one galaxy. Can you see it in the upper? That's NGC 1068 or M77. That's that amazing AGN. He's spectacular. He's got a very different colors, and he's powerful. He sticks out in every way imaginable, including it has an incredibly high surface brightness. On these plots, that's the left side. High surface brightness is left because that's a magnitude. Bulge to total, I'm not going to go into that. Here's a tabulation of mass, the stellar mass. And I just want to point out who the biggest and the baddest in town is. So here's a histogram of stellar mass and diameter. And you'll see it's NGC 1316. That's Fornax A. It's, yeah, why is it big? Well, it's eating everything in sight. Look at these, look at the picture in the upper left, which is a deep optical. The lower right, you see the radio. Those are incredible jets that are coming off of it. That's why it's such a bright radio galaxy. So this guy's a monster because it's eating everything in sight. It's quite spectacular. And he weighs a lot. He's a lot bigger than the Milky Way. We could put it all together with this neat, nifty diagram where we put star formation versus the mass. So this shows the evolution, the secular evolution of galaxies. And the upper part, the blue part, basically shows what normal galaxies ought to do. They should start from the left. They're little babies. They grow with time. And they move to the right as they grow. They get heavy. And their star formation goes up. They become adults. And they really burn bright. And then when they become older, like me, they start to get tired and they fall off. And such as the Milky Way. The Milky Way is in there, if I could only show you with my cursor, but he is sort of where the green things are. And then when you're old and you're just about ready to fade away, you turn red. I did want to point out here that NGC 1068 is also sticking out. He's at the top. That's the AGN. And you know, this is what it looks like in the optical and deep optical and the infrared. You can see it's got incredible stuff going on in its nucleus. Amazing galaxy. So what's the upshot? Is the local universe different? Is it special? Well, no, except for the one thing. 1068 is special, I will say that. Okay, I'm at 50 minutes. Marius, if it's okay with you, I want to mention one thing. Because
you still got to rain, that's fine, you can still carry on.
These are neat. These are called pinwheel diagrams. And essentially what they are, they're thumbprints for every galaxy. And so take this one. This is M82. This is the fireball. Remember that? This thing is a starburst. It's really doing some amazing stuff. But what my pinwheel shows is I take all the physical parameters that I can measure and things like the colors, the star formation rate, how big it is, the diameter, its surface brightness. And you put that all down on these pinwheels. Now, the pinwheel, the way it works is in the center is what I call an average value. So the bullseye is where most galaxies land, such as the Milky Way wouldn't show much. It would just be in the middle. It's average, it's boring. Galaxies that stand out will start to show these vectors. And they'll show them either red at the top or blue at the bottom. So red means they're outstanding, and blue means they're the opposite. They're miniatures. So M82 in this case has a high surface brightness. That means its nucleus is really, really bright for the area. So it's a lot of stuff is happening in a small area. And that's because of the starburst. It's got what I call warm and dusty colors. And it's got a hefty star formation rate. That's a log. So it says 1.0 there in the middle. That means it has 10. Star formation rate 10. That's high. The Milky Way, for example, is about 1. And so here's an example. So you would look at this and you'd have sort of a picture of what could be going on with M82. Here's NGC 1365, which is a big barred spiral in Fornax. How do I know it's big? Well, look at the pinwheel. The pinwheel shows you that it's monstrous. It has something like 70 kiloparsecs in diameter. He's a big boy, and he's got a high star formation. That's because he's physically large. Warm colors, and its mass is it's got a lower mass than than the Milky Way. So he's still building. And now just to show you that sometimes galaxies are a little on the dwarfy side, this is a little bugger. And you can see, maybe you see a bunch of blue there in the pinwheel. It's got a low surface brightness. That means its nucleus can be barely seen. There's not a lot going on in the nucleus. It's got a low mass. It's a dwarf. And it's got stellar colors, and its star formation is hardly there. So this is the sort of new thing that we've created, so that you can imagine that you can flip through these things and use machine learning to actually find birds of a feather, if you will, things that have similar properties. All right, this is my last slide. What's next? This has all been published, but I'm now about to publish a bunch more. You know, I have 130,000. I'll probably do a subsample of that has some particular science goals. For example, it'll be volume limited, flux limited, might even be size limited. But anyway, that's my next. And then for the long term, my next several lifetimes, I'll be measuring the other billion galaxies. Thank you.
Thank you so much, Professor Jarrett, for sharing your presentation with us. We really enjoyed it, and I'm sure that we got a lot of questions coming up. So what I'm just quickly going to do is.
Would you like me to stop sharing and we'll just face to face?
Yeah, absolutely. That's what we're going to do next.
Okay, so I'm going to turn off my sharing.
There we go.
Did you do it for me?
I did it for you. Great. Thank you very much, Professor Jarrett. We really enjoyed your presentation, and thank you so much for taking your time out to come and speak to Cape Center. I'm sure that
you're most welcome. I hope it wasn't too much. I did pack in a lot of stuff because, you know, it's fun.
Well, actually, the funny part is I was thinking we could do another hour.
Yeah, it goes on and on. Believe me, there's a lot of galaxies.
Very, very, very interesting topic. So once again, Professor said, from the Cape Center Committee and the Cape Center members, thank you so much for joining us. What I would like to do now is open up the floor to the rest of the attendees, and you guys are welcome to ask Professor Jarrett some questions by either raising your hands in the Zoom meeting or by just verbally indicating to me that you've got a question. So if you guys have got any questions, please fire away. So Chris, you're up first. How are you doing, Chris?
Yeah, thanks. Thanks very much for that. The question is, what is the largest galaxy that you know of? Not close by, or maybe far away, but and how does it compare to, say, Andromeda?
So first off, let me just say what Andromeda, how big it is. I should have showed the pinwheel for that. Andromeda is big. It's a little bit more massive than the Milky Way, but they might as well be comparable. It's a little bit, I'm going to call it a little bit older. It has a morphology that's what we call early type spiral. It has spiral arms. They're tight, as you know. In the optical, M31 appears flocculent. It's very difficult to understand it, but in the infrared, you could punch through it. It's an early type. It's fallen off that galaxy main sequence I showed you. So he's sort of in its final. He's in his late middle age, still forming stars, but not for much longer. And it's growing, but it probably won't grow much bigger than it is. It's a little bit bigger than the Milky Way. So we're talking 40, maybe 50 kiloparsecs. I don't know. Nobody really knows in diameter. So he's not a little guy. I just want to point that out. He's not little, nor is the Milky Way. If you were to look at the local group from far away, you would see the Milky Way and Andromeda. You call it a galaxy pair, which we work on. You'd say, oh, there's a nice little galaxy pair that's 100 megaparsecs away. And then when you look really close, you'd see M33, and then you wouldn't see the dwarfs or anything. Now, as far as size goes, we know, so that's a really good question. We know that there are galaxies that are 100 kiloparsecs across. And the thing about size is that that 100 kiloparsecs is really dominated by gas. So hydrogen gas, the primordial gas that's formed with that in the halo of this galaxy, and the dark matter. What's called the star-forming disk is much smaller. It might be 50 kiloparsecs or something. It might be Milky Way like. That's where the stars are forming, and that's what you'd see with your telescope. But we, with our big H1 telescopes, can see that the galaxy is actually 100 kiloparsecs across. So that's one thing, and we do know about these galaxies. I studied one of those many years ago, but there are also these monstrous galaxies like NGC 1316 Fornax A, where they're really big because they've been eating galaxies as they've gotten more massive. But they also, because they're accreting galaxies and stuff from their environment, that means it's almost like they have no size. They just keep going as big as the local region will allow. And then, so that's local. That's the local galaxies. And then there's the high Z things, which there have been reports of galaxies that are twice as big as that are just these monstrous things that, but most people don't believe it. We think that it's because of the angular resolution issues and the bias coming from whatever wavelength they're looking at. In fact, you're looking at multiple objects. So in fact, that's a problem. When you look back in time, you look at high Z galaxies, is that when you get a spectrum, you do a redshift or you get a measurement, you're often looking at more than one galaxy. You're looking at a few that are in your beam, right? So if you looked at the local group far enough away, you would be measuring M31, the Milky Way, and M33 all together, and you'd be making one grand statement. Wow, it's a really big galaxy, you know. So I don't know. I waved a lot of my hands a lot there, Chris.
Thanks.
Thank you so much. That is actually quite a interesting point that you've established, that you don't really think about if you really had to look at it from a very far distance away. How do you separate it? Right, let me see. It's just a question maybe that I would like to ask from my side. It's right in the beginning of your presentation where you were giving us a bit of an overview of all the galaxies. You know, there was the point that you said, you mentioned the Great Attractor, and then you said, yeah, we can talk a lot about that. Maybe no, that's the point that we can just sort of maybe divulge a little bit into.
Well, so I kind of give you, when I fly around the universe, I have to remind myself and my students that that's static. We're seeing a snapshot in time, boom. But in fact, every single galaxy is moving with respect, not just the flow, but it's moving with respect to its local environment, because it has these little potentials all over the local universe. So galaxies flow towards these potentials, okay? So those are called bulk flows, right? And that a bulk flow means a lot of galaxies sort of like going off in one direction. Now, if you live in a cluster like Virgo, you have a flow, you have a motion that's due to orbiting the gravitational potential well of Virgo, okay, which is thousands and thousands of galaxies, right? And so you zip around, zip, 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 and then we see that radially, because that's what we measure, the radial direction. And hence that's how you get these fingers of God things, it's called peculiar motion. When you put a lot of peculiar motions together, you can get these vectors. But when you're talking about bigger areas, bigger than Virgo, and they're all going towards one direction, that's called a bulk flow. And why? Well, that was first discovered in the 80s. First discovered with the redshifts. Nobody else knew about these things because there's no other way. You need kinematic, right? So it was the redshift surveys, and only radial, keep that in mind, no transverse. And so they start seeing these things, and they noticed trends. And the biggest trend by far was this thing they just named the Great Attractor. It was great. It was, I don't know, and it was stick up. And there were other attractors, Virgos, an attractor of Perseus, Pisces, supercluster, but it was sticking up twice as high. Think of it as like peaks of a mountain. and it was sticking up above, and they're like, what the hell is that? Now, what made it particularly mysterious and fun is that it happened to be in the galactic plane. So that made it really hard, and so there was a lot of, well, there's something monstrous hiding behind the Milky Way that we can't see. It's being blocked. And so since then, in the late 80s, there's been this huge effort to unveil all that, you know, what we call the zone of avoidance. But it's really the zone of obscuration is what the way to think of it. And so we've been peeling that apart. And lo and behold, the Great Attractor now, because that's what you asked about, what's going on there? Well, there's a big cluster there, first off. It's called the Norma cluster. So in the Norma constellation. So you guys can probably go look at it, but you probably just see the Milky Way in the way. So the Norma cluster, but Norma cluster is big. It's as big as Coma. Coma, by the way, is like the biggest cluster in, you know, locally. So it's a monster. So he's big. That's the first point. But there's more. And one cluster won't do it. I can see that, Marius. You're going, ha, one cluster, big deal. Well, that's because it's only part. Clusters in the cosmic web. I wish I had a better picture. I didn't do you guys justice. But the cosmic web is a web, and the nodes of these webs, which are filaments, yeah, those are clusters. So the cluster is attached to a filament, and another filament, and another filament, and that's the Great Attractor. And but we ran into, eventually we did our best with the infrared, but we've hit the wall. And the next way to go after this thing is with hydrogen, a hydrogen line, because it's radio. You can see through the gas and dust. It's redshifted. You can find the line, and so that's what Meerkat's going to do. That's one of our key. And invite Renee Kron-Kordovig to this. She can tell you about it.
I think Kitchel's taking notes. Thank you very much. I mean, that is a topic that I think we can discuss for hours, because it's really fascinating, just thinking about, you know, motion. Kitchell, you've had your hand up. Thank you.
Actually, Tom's just answered one of the questions that I had, but the second question was about Nathan Dake's three-dimensional video there. And you said that there were 4 molecules. 4
particles. No, sorry. N-body simulators talk about particles, which isn't necessarily a star, but it could be a bunch of stars. But they're a packet, okay. And these 4 types of objects or packets are physically meaningful. For example, one of them was stars. One of them was the bulge stars, not the disk stars. So disk stars, bulge stars, okay? Another one was the gas, right? And the final one was dark matter, right? And it's all distributed according to what we know how galaxies are made up, right? And so you don't do these N bodies unless they're actually physically motivated and they make sense before you smash them into each other, okay? Sorry about that, I went over that so fast. And so those 4 different types, I do in my hands like this because there's 2 different galaxies, 4 of those types of galaxies, and they're colored, 4 colors, 4 different colors, so 8 colors, right? And they go, and they do their thing and they start mixing, because we're gonna find out where's the dark matter going. We have no idea, right?
Okay, thanks. No, I just wondered what those things were.
Yeah.
Excellent. Thank you so much for your question, Ketchel. Next, I see that we have Richard. Richard, you had your hand up. You're more than welcome to pose your question, please.
Hi there, thanks. That was very interesting. Tell me, rotational period. Are you able to determine the rotational period of any of the galaxies? And if so, what's the shortest and longest in, say, one cycle per how many million years?
Well, I can tell you what their velocity is because I haven't calculated what their period is. Sorry about that. But what we do when we do this kinematics is we calculate. So remember in the movie, I showed you the kinematic movie, so M31, and you saw the gas spread out. So that's you actually see the gas receding from you, the redshifted, and you see the gas coming at you. That's just the disk doing this thing, right? So that's the kinematics of the thing, but spatially spread out so that you can see it. Now, traditionally what you do is you smash that together and you create what's called a rotation curve. So that's the radius in kiloparsecs versus the velocity of the gas rotating, the velocity in kilometers per second. And so what you see is you see the Keplerian, near the nuke, near the core, you see the Keplerian rotations. And then you see it roll off. And then you see the thing that baffled astronomers way back when they started doing this, and they see it going flat, right? What it should do is fall off in a Keplerian way. And instead it flattens out, and that's been the, dark matter is our best bet of what that could be. But this is what, so we characterize that rotation curve, and so you know how fast that gas is moving at that radius. And so, okay, so you can go ahead and then calculate what that period is. Sorry, I don't have that. I think that's a good idea though, because that might be a fun thing to have, because, but it depends where you're going to measure it, right? So, are you on the outskirts? Or often what radio astronomers do is they take the max where the thing peaks. Sometimes it comes down a little bit and flattens out, and they say at the peak max, this is the velocity at this radius, and then you can calculate the period of that.
Thanks, that was really interesting. How does the Milky Way compare? Is it average speed or fast or slow?
No, Milky Way is pretty massive. It's 10 to the 11th stars and 10 to the 12th total mass. So it's booking, right? It's 300 kilometers per second or whatever it is. It's a lot. It's going. It's a big boy. It's all determined by mass. Yeah. So he's out there, and those are my favorite kinds of galaxies, are the massive ones, because you can measure things. They do interesting stuff. They have star formation, and the kinematics are amazing. They're beautiful. Whereas dwarfs, they might do 50 kilometers per second. Barely moving. In fact, you can't even tell they have a disk. Sometimes these things are just disturbed. It's not my field.
Okay, thanks a lot.
Thank you so much for your question, Richard. That was a very interesting question. Next up, we've got Kevin. Thank you so much, Kevin. You're welcome to pose your question.
Hi, thank you very much, Professor. Wonderful discussion there, wonderful slideshows. Just two quick questions. Number one, what do you call, and is what you call the local, local galaxy groups the same as what the rest of the cosmological world is? In other words, up to how much? A few 100,000 kiloparsecs, megaparsecs, gigaparsecs. What do you call local? Yeah. Okay, so let's. I love questions like that. I teach a class, a master's class, extragalactic astronomy, and that's the sort of thing that gets me excited. I start doing an Irish jig, but I won't do that here. Because it's a Zoom call. Yeah. So first off, the local group. It's about a megaparsec. With galaxies, you have to switch over to megaparsecs. And the reason is because the nearest galaxy is about Andromeda, and it's about 1. It's 730 kiloparsecs, but it's about 1 megaparsec. And the local group's about that. Now, the reason what we really mean by the local group is that they're gravitationally bound. Yeah. And there are groups nearby, 3 megaparsecs away, M81 group, M83 group, just a little bit further away. And so they exist, but they're their own little thing, right? They have their own little groupie going. And it seems to be about a megaparsec. So it depends on the mass of what you're talking about. The Virgo Galaxy cluster is several megaparsecs in size, many, 5. Yeah, so it's really the radius out to which your local group doesn't affect another group, or seemingly doesn't affect the next group.
That's right, gravitationally, or is it gravitationally bound is another way to put it. Yeah, and there could be objects that are not bound, that are just passing through the local group, but we could figure that out with their kinematics if you look at it. Cool. And this is not my thing, so I can't tell you if that's the case. we know that we know that in other groups, which I do study, that galaxies, they have what are called penetrators. A galaxy comes through and it creates havoc. It creates a tidal disturbance. And that galaxy that went through may not be bound. It might keep on going, or it's in a highly long elliptical period and it'll come back. And anyway, groups are a lot of fun. They're a blast. So so bound. But but the other definition it gave for you, which was the local universe, is completely different. Not gravity. It's the fact that as you move into the deeper universe, you're starting to get into what are called evolutionary effects, right? The galaxy properties themselves change because you're looking at a different period, and that's and we know that around a redshift of 1/2, that's certainly true. We know, and redshifts of 2 and 3, that's the age of star formation. That's when galaxies were going mad with forming. That's around redshifts of 2. But so redshifts of 1/2, we know galaxies are doing stuff. Somewhere around, I want to say redshift of 0.2 or 0.1, I think you can comfortably say that's our posse, that's our gang.
And that's still pretty fast. 0.1, 0.2, it's still moving. That's moving fast, relatively. It's probably what, I don't know, 20, 30,000.
30,000 kilometers per second. Yeah.
So that's not
no, indeed. And those are far enough away too, right? That they're starting to get hard to decipher. And so I consider redshift 0.1 kind of where we do a lot of our, for example, our H1 work. We'll comfortably do within 0.1. Meerkat's super sensitive. It can go deeper than that, but we can do what I call resolve stuff. We can actually see that there are. So I can go on and on.
Yeah. And the second part to that, and I'll be very quick, sorry, is you were talking about the Great Attractor and all of that. When we line up those, or when you, other cosmologists, line up, astrophysicists line up the huge view of the universe, with all the filaments, does our attractor lines, or the calculations from just the mass alone, I kind of know the answer, it's a leading question, but I want you to tell me because I might be wrong, do they actually line up along those filaments? In other words, because we know that if those filaments are showing mass only, then there's something wrong with our dark matter theory, or, do you understand what I'm saying? In other words, because,
this is the ongoing research, in fact, and it's why, a lot of there have been multiple waves of research activity in large scale structure, and I'm going to say the first wave was in the 1980s with the first redshift surveys, and you maybe remember the famous Stickman redshift thing, and that came from that era, and then everybody got super excited, and then the theorists jumped in and they were doing reconstructions of the local universe, the density, these attractors that I said. And that's 1990s, so you can read that. And then things fell off because essentially what drives research is data, new and better data. And then the data stopped. And so nothing happened. So it became a really slow burn at that point. And large scale structure studies sort of, they went into the background a little bit. And then the next wave of redshift surveys started, like Sloan, for example, SDSS. And then you had a new wave, and remember I said the Great Wall, part of Coma and the Great Wall was seen in the original ones, and then now Sloan can see the next Great Wall, which is way bigger. It's way bigger, and that's still nearby. So anyway, the local universe, we're just what I'm trying to get across to you is that we're still just figuring out how to do this. The first wave was tantalizing. The next wave was Sloan. We start to do real science, quantitative science, like 2-point angular correlations, which you've probably done. We've started to do how things cluster and clump, kind of thing. I wrote a paper.
But my question was, sorry, but are those clumps purely physical mass alone or dark matter, or are we still not at the point where we can not definitively say, I don't think we can, but can we say with 98% that yes, dark matter are in those clumps, therefore that's why the universe looks like this on a large scale?
Yeah, well, so dark matter, the only way to, dark matter is tricky. You have to use lensing to do this, as you know.
So there's strong lensing, there's weak lensing, and this is cutting edge research happening right now. The first lensing surveys, which happened a good 10 years ago, are the first sort of dark matter maps that we ever saw, right? It's indirect that we've seen them. And so we start off with saying, wow, for sure, there's dark matter, they see it. And it's slightly offset. It's not necessarily right on top of the light. The light, right? The lighthouses, which are galaxies, and that's called the bias factor, by the way. You probably know that. Anyway, and so now the new cutting edge stuff. So you probably know about some of these. There's these exotic, super duper low surface brightness galaxies that don't seem to have dark matter, right? And so they're going, what the hell is going on? Everything has to have dark matter. Thing is, I don't know what the answer is. I think that right now things are looking pretty consistent that those lumps and bumps have dark matter, and of course they need them. These cosmological models won't work. You've got
but they are finding, but Professor, they are finding a lot more mass than they thought. It's not 5% anymore, because all these invisible galaxies, if you add them up, it's like an integral. They're actually probably more than the ones we can see. Anyway, we're moving on. We're tangential, but thank you very much. Wonderful.
Yeah. No, you're right.
Of cosmology.
It's fascinating stuff, and I follow it myself. It's not my thing, but I do follow it because it's very important to know. I want to know, are my cosmological models I'm using, lambda C, cold dark model, I want to know, is that right? Because it's important for how we map our galaxies. And if it turns out to be wrong, if we got it wrong with dark matter, if it turns out that the bias factor is completely different, which is how the light relates to the dark matter, how that relates. If that turns out to be wrong, because that's the assumption everybody makes, then we have to go all the way back and retool. And you know what? We might be on the cusp of that happening, where we fall right off the cliff and we say,
well, it's like Einstein. No one believed him in the beginning. He didn't believe himself, and now it's so you could be doing at UCT the stuff that you're doing now on local galaxies could actually end up maybe refuting something, and then actually they'll come back in 50 years' time and say, Professor Jarrett, he was right on the small scale. We should have listened to him. Anyway, thank you very much.
Yes. One quick thing about that, I don't do this, but I have colleagues that do this, and they've tested using H1, using the hydrogen and kinematics. They've tested MOND, so modified gravity, and they've ruled it out. Every single experiment rules out MOND, left and right, left and right. I'm kind of against MOND now, but that said, things are moving fast. So so we'll see.
There's so many theories. It's like everyone's got an opinion. But in the end, will we be old enough? Will we still be around to know the real truth? Who knows?
I hope I am, because I'd like to know. I'd like to know that the whole H0 thing. What's going on with that? The Hubble constant. Anyway, go on.
Sorry there, Marius, for taking up most of your show here.
Thank you for your question, Kevin. Interesting as always. Right, to the rest of the audience, is there anyone else that would like to pose a question? Yeah, Richard, you got a question?
Oh, hi, another question, general question this time. To what extent is the latest increase in the speed of computers every year helping your research?
I'm going to say it's awesome. I'm going to give you two answers, though. I'll give you the left hand, the right hand. My left hand says, man, I tell you what, I started off, let's see, I was in grad school in the 80s, and we had a computer called a VAX, and we did stuff, and but our data, what was coming off our instruments, our telescopes, we had these new CCD imagers with 2048 formats, and that we could barely keep up. But the computers got faster. They just exactly as I was, going through grad school and coming out, they got so much better. And then the workstation showed up, and the workstation is where you see the GUIs and the graphics windows, and that showed up at the end of my
grad school. And so I got to launch as a postdoc with all of this new technology. And the faster computers have been nothing but help. I will say that, nothing but help. Now, you know that the data, now these days, the data is getting so big and complex that people are now drowning in it. And they feel as if we're going to need to use these machines to do more, which is where the machine learning and artificial intelligence stuff comes in. Now, I think that works sometimes. I think sometimes it only fools you. So I think that's a complex picture when you think about how we use computers to interpret our data. I think that's very difficult question. But that's why I'm so big a proponent of visualization, because in the end, you got to check, right? Don't trust the machines. Don't let them run amok, take over. You'll be sorry.
Okay, thank you. Ever foresee a time when the machine learning and artificial intelligence will do the whole thing, including writing the paper at the end?
I don't see that happening. I see it getting pretty far where it could chug, and then you could do statistics, chug, and you get some plots, but it won't write the paper for you.
Right.
But it can get it all wrong, so you better know what you're doing. If you just rely on a black box, I try to teach all my students, understand what's going on in the black box. Because if you don't, then you're helpless. It spits out something and you go, thanks, okay. You know, but most of the time they get it wrong, these machines. They're really dumb. They're only as good as the programmer.
Yeah, that makes sense.
Thanks for your question, Richard. I think that's sort of really tied in, because as you were talking through your presentation, you were talking about machine learning, and we very recently had a lecture by Dr. Michelle Lochner, which basically covered. Great. So she basically covered machine learning, and I was trying to, think, how do you guys interface, because yes, I think that you've got a very, very valid point. There is a line that you've got to draw in the sand, up to where do you trust the data that you've received from the AI. And, I guess, as things progress, that margin will progressively move along, but there's still a point where you have got to draw the line and say, okay, how do we as humans interpret this? But
yeah, no, for sure. And Michelle's great. I actually talk to her whenever I can. She visits. And she knows that, and she's also tries to keep her eye on the data. So she's both. She kind of bridges the two to make sure that there is this nice synergy between the human, the researcher, and the AI. Because you've got to do that. You've got to do that.
Excellent, thank you. I think just maybe one last question that I actually want to sneak in is the interaction of your work with the Ezekiel Planetarium. I remember when the digital planetarium opened up, we were all privileged to go and have a little behind the scenes peek, at what they've got going on down there. And, even the little bit of science behind astronomy, where they were doing some medical research, and been able to project those images onto the screen.
Yeah.
But tell us a bit more about your work there.
Did I give you the tour, or was it my postdoc, Lucia, or
yeah.
Sally?
Yes, yeah, it was Lucia.
Yes, to all three. It was Lucia. That's cool. Yeah. I don't think maybe I'm giving the wrong impression to the group here that like I'm doing all the work, but it's a team, right? I direct a lot of stuff. Sometimes I'm just a lowly collaborator, but there's a lot of people involved with all this stuff. Now I have two postdocs, Lucia and Sally McFarland. You may know her. She's an amateur astronomer too, and Sally. And they take care of the planetarium. So Sally is our liaison. In fact, her job is to make sure that researchers are able to use the equipment and so forth. So she loads up a lot of the data sets. Lucia is sort of my project manager, but she's also just stands in for me when I'm not around. And so we've been putting our data sets, three-dimensional data sets up there. Basically, when we publish them, we start putting up there, and then we can give a talk to our colleagues, or sometimes we've had conferences there. We had a big one back before COVID. We just snuck in a big meeting of astronomers. It was observational cosmology, in fact. And it was really exciting because I got to show, everybody showed different things on the dome. It was neat. So the dome is a really beautiful, amazing venue for doing, for showcasing and demonstrating stuff. You can do research with it too as well by simply visually looking at things, because it gives you a view that you don't get from a machine. Although these days I think VR is even better, because the way VR gives you the power of the interaction. I can manipulate the data much better than what I can in the planetarium. But the planetarium is not for that anyway. It's all about having your colleagues come in and flying around. And you mentioned the medical stuff. So we've worked with the neuroscientists. So Lucia showed you a brain, a cranium in 3D, and also the molecular and cellular biologists, where we showed you a cell, where we're studying the pathologies of cells, that sort of thing, cancer cell. And those are called volumes. So volumetric data. And I showed you one volume here today. That was the Spectral Cube of MEN 31. But volumes to me are just so much fun to work with. But they work great on domes. Fantastic. Yeah, so the dome is closed now, but I think it's going to open soon again.
Yeah, we hope under lockdown level 1 we're going to have a little bit more access to these type of facilities.
Yeah, and we'd be happy to, if you guys want to have a meeting there sometime, do another one there. We can do that.
Well, we may just take you up on that. Be careful.
Mondays, only on Mondays.
Mondays, excellent. Well, Professor Jarrett, thank you very much for taking your afternoon out to have a conversation with us and do your presentation with us. I would also really like to thank the members of Cape Center and the friends of Cape Center that has joined us in this presentation with Professor Jarrett. What I will be doing is I will be uploading this presentation to our YouTube channel, and then I will share it to the general public. But yeah,
great.
Thank you once again, and please feel welcome to stick around. So thank you so much, and we wish you a pleasant afternoon.
Thank you so much. It was a pleasure.
Thank you once again.
Okay. It was great. Thanks.
You're welcome.
And thank you, Ketchel, for once again organizing an excellent speaker for us.
Well, we would be going to actually visit the VR labs at IDEA if it wasn't for this this plague.
We can handle about 5 people if you want to. Yeah, I'm happy to do that too. Our lab is even better. Well, no, they're both good.
We'll start a raffle for visiting the tickets.
Yeah, or 5 at a time. We can rotate.
Thank you so much.
Before you, I know you're probably desperate to run off, but I'd really like to say that I'm so pleased to hear that you're skeptical about computing, and that students really need to know about the innards of this box. Yeah. Not a black box.
Oh yeah, oh yeah, and another thing my students do all the time, not just the black boxes, is that they'll go off and they'll generate a plot, especially if it's the first time they generated that plot. It's wrong. There's something wrong in it, or it's completely wrong. Is that I always tell them, I say, assume it's wrong, go find why it's wrong, fix it, and then bring back a better plot to me instead of showing me something that's crap, right? It's better to figure it out yourself. But that's the process of learning. So we do that. You'd be surprised. Seasoned scientists like myself will make a plot, the same plot 100 times. All those plots that you saw have multi-generations of, I'm tuning, I'm getting them right. I did something wrong here, or something like, what the hell's that? That kind of thing. And so it's why is it wrong? Well, the program, the black box, Python, whatever it is they did, had a bug. Their programming, that's fine. Yeah, so we programmers always say to ourselves, when you have a program that's complex, you say, there's a bug in it. I don't know where it is, but I know there's a bug. And you find it, you stamp it, and then you say, there's another bug in there. I don't know where it is, but I know it's there.
Yeah,
and that goes on really forever, your whole life of that same bloody program until they're not appearing anymore. Bugs, you know.
Yeah, but I mean, some of it can be very, very deep down. I mean, it can be with the floating point unit and how it interacts with your, your
Yes,
that's
you can have design flaw. The software has a flaw, a design flaw. It could have a bug. It could have something insidious. You wouldn't necessarily call it a bug, but it rears its head occasionally, and it does it for really odd reasons. Again, you would say, well, in the end, you use bad programming practices, et cetera, et cetera. But you know what? We learn from making mistakes, right? Mm-hmm. I think it's important for educators to guide your students in how to recognize mistakes or problem solving, right? Problem solving, the number one thing that you've got to teach young people in South Africa. It's problem solving, and as part of that is the process of troubleshooting, recognizing issues, and digging into it, right? Dig. Because I think maybe the way people are educated, is when they're younger in the primary system. To them, everything has an answer, right? You just look it up in a book; it has an answer. That's not true in research. We don't know the answer. We just kind of know a trend. We know what might be the answer, and so we look for consistency. Yeah.
Young people trust these machines. They won't.
Yeah, they do, and so it's up to us as the educators to say you shouldn't. Mm. They're a tool. Mm. Use them. Don't let them use you.
We in Cape Centre were purists. We like to put our eye next to an eyepiece, and there's just nothing between us and that M31.
Yeah. Well, my philosophy is go look. So when I have a student say, "Look, show me something on paper that's weird," and I say, "Did you go look?" So, for example, a common foolish thing to do is to say, "Hey, professor, I found something new. I'm going to get the Nobel Prize. Look at this object. It's nothing like it's been seen in the universe." And I don't even have to look at it. What do you think I'm going to say? It's an artifact. Bogus. Go look. Did you look at the data? Oh, yeah, I looked at the image. Did you look at the raw data? What? What's that? You know what I'm saying? Sure enough, it's a big meteor streak. Right? Didn't get cleaned up in the further on and so forth. So artifacts are the number one bugbear of research scientists anywhere in the world, right? We all even famous people have been fooled, and they've published papers and claimed 3 sigma detections and so forth, right? Whereas it was a systematic or a bug in their code or, something. So yeah, danger.
Devil's in the detail.
Sure. Yeah.
Thank you so much. I would actually like to ask Oka, who just finally managed to actually find a camera in somewhere in his study, to maybe just share with us a little thing that he's been busy with as well, with regards to Heritage Moon. Oka, are you still with us?
Yes, Marcus, thank you. You and Ketchel have put me terribly on the spot because I didn't have anything prepared. Marcus, can I share my screen?
Yes, you may. I'll make you, just give me a second.
So it's not so much that I've been busy with stuff. It's this is a project that Ed Foster has been running, and I'm super excited about it because one common problem that I'm sure all of you have faced if you ever dealt with the raw public is they phone you up and they ask you, when can we see the wolf moon, and when is the sturgeon moon visible, and why is it called the strawberry moon, and so on. And if people Google, then they find all sorts of nonsense, and so they find these so-called traditional moon names. I mean, these names aren't traditional unless you count the 1820s as tradition. It's a pastiche of various indigenous people in North America. And it's not as if there is a council of North American indigenous people who can ratify this is the list. It was sort of made up. And this is what people think the moon in August should be the, I don't know, the strawberry moon or whatever. So our thinking was the full moon is gorgeous to look at. And it's one of the things that you can tell the general public, you know, in your WhatsApp group, you can tell everybody in your single or in your street, oh, go outside now, the full moon is up. And they all, you know, all find it most nice. But we thought that this would create a wonderful opportunity if we can connect this beautiful sight in the sky with something to do with South African heritage. So we can celebrate something about South Africa as opposed to, you know, talking about the wolf moon, because there were never any wolves in Africa. We've got jackals and wolf as the stories in Afrikaans, but there were no wolves. There was a kind of wolf millions of years ago. You can see part of its skull and bones at the West Coast Fossil Park. But that's kind of like, you know, sort of stretching the thing. So anyway, so we came up with a list of 23 moon names. So it's 23, 12, one for each full moon in the month. And then that insipid name, blue moon. So some months, most months except February can have 2 moons. But February can never have 2 full moons. So that means there are 23 full moons possible. So then the challenge was to try to figure out, well, how do we choose names for moons that is not going to offend more than 9/10 of the population? Because if you ask, how do you say what is definitively South African, you're going to get everybody upset. So the strategy we chose was to say, but hang on a second, if we take the concept of South African, now this can be any nation actually, and you ask, how can you break that down into its principal components? Then, to my way of thinking, those principal components are people, the environment, and the interaction between people and the environment. And there's nothing else. Anything you can say or mention is going to be in one of those categories. Unless somebody comes up with a counterfactual now, and then we'll have to restart 3 months of work. But as far as I've got it, anything can go into one of those 3 categories. So if we select names that touch on all 3 categories, then we've covered all possible bases. Then we haven't left something out. We haven't you know, disrespected sport or belittled religion or whatever your pet hate is. So with that as the guiding principle, we then came up with the names that you can see behind me. And if you, Morris, can I quickly screen share because I think that my stream rate's a little bit low.
Okay, you have got co-host permission, so you may share.
Thanks. So if I'm not mistaken, you should be seeing my web browser now.
Yes, we are.
Okay, so if you head on over to the center's website, you'll see Heritage Moon is quite, you know, is pimped at various places. If you click on the link, you'll get to the Heritage Moon main page, which I'll get back to right now. There are a couple of links on this page to other things. For example, all the full moon dates for you in a calendar form. So you can see in 2022, there's the Mantis moon is on that date and time, and there's even eclipse there in the frost moon in May. We've got one little page on observing the moon because our focus is astronomical heritage, but sometimes people don't know where to find the full moon. We all know this. We can't believe that people don't know where East is, but you know, East is apparently a matter of opinion. So we've got a little bit of advice on just basically how to observe the moon. A gallery of moon photos. These are mostly by Angus Burns, who's a really good photographer. And then we quickly delve into the once in a blue moon story. It's still unclear to me where it comes from. This, I think, is quite an interesting plot. It shows the incidence of the occurrence of the phrase once in a blue moon in the corpus of printed English texts. So we see that the earliest mention of that phrase is around about sort of 1820s or so. And then something was going on here in the 1930s where everybody was talking about once in a blue moon. And it seems like we are, much like COVID, going into a second wave here, which seems to be flattening down. So it is still very much an open question where once in a blue moon, or the concept of a blue moon, comes from. What I actually wanted to show you, if you go to the Heritage Full Moon page, nice photo by Angus again, and then we've got a handy table giving you the names for each of the moons, both for the first and the second. And then you can find the individual moons listed here. So where are we now? We are in September. So we can see in September, we've got the spring moon. And if you follow that link, you'll get a description of what and why and what goes on with why this month was chosen to be a spring moon. A little bit of background of various things in South Africa that relate to spring. Spring is a bit of an easy one because, you know, it's tied to what the Earth and the Sun and our orbits are doing. But I think next month, the next full moon will be the whale moon. I think it's a great name for a big moon, is the whale moon. The second one will be the elephant moon. So the idea with this is to leave people with astronomy outreach people, to leave us with a framework around which we can maybe build the events for a month. And also to just, when you tell your neighbor, you can say, you know, well, that's the full moon tonight. Okay, did you know it's the whale moon? And then you can say something, if you go and read our handy website, you can maybe say something interesting, one little fact. You don't want to overload people. Just one little fact about the whales and how they have played some influence in South Africa in terms of economics, wild animals, conservation, and a whole lot. So all the themes that we've identified, those three primary ones and the subdivisions, are expressed in various ways across the moon names. So hopefully we will end up irritating everybody. Not everybody's cross with us for the name selection, or everybody will love it. And if anybody from the Cape Centre has got any opinions and feedback, please, as always, let me know. Everything is a work in progress. Thanks, Marius.
Marius, you're muted.
Marius, I think you're actually muted.
My good God. You know, we've got a thing at work, you know, called the mute monster jar. So I think I'll have to make a serious contribution. Thank you so much, Oka, for sharing what you've been busy with as far as your Heritage Moon project. And I would also like to thank Professor Thomas Jarrett for sharing his afternoon with us. I'm going to give you guys one last round for anything, or for any questions, or for any appraisers. And then I'm going to say, right, I'm going to formally end the meeting. So are there any other comments? Right, thank you so much. So guys, this then formally brings us to the end of tonight's meeting. You're more than welcome to stay on and chat with each other. I will be keeping the channel going for quite a while. But to the rest of you, thank you so much for joining, and have a pleasant evening.
Bye, everyone.